let's write down the eigenvalues of H1 and H2. Okay? So then we know completely all the information we have for the alpha 1. So it was 2 and minus 1. Alpha 2 was minus 1 and 2. And alpha 3 was 1 comma 1. Okay? So these were the eigenvalues with respect to H1 and H2. These two numbers. And of course, the minus alpha 1 will be just the minus alpha 1 would be just minus 2, 1, just the negatives of that. Minus alpha 2 would be plus 1, minus 2, and minus alpha 3 will be minus 1, minus 1. Okay. So these were the eigenvalues, and then we plotted them just to see the figure, what kind of, in the two-dimensional space, how this will look like. Now, in this basis, it was not so nice, right? However, then we went to the basis for H1 and lambda 3, lambda 8. Lambda 8 was, I don't know, I forget now. 1 over root 3. 1 over root 3 times
2H1
2H1
plus H2
plus or minus? Minus.
Minus. This is plus. Maybe the opposite. Plus.
Plus H2.
Yes.
Okay. So there was this. So once you go into that, then all the figures we drew was exact regular hexagon, right? Yeah, 6 points, and we saw all these nice symmetries, reflection symmetries and things like that. Okay, now what we'll do is we'll go to the fundamental representation. So adjoint representation was there. Before I go into that, let me say the following. Now, okay, should I do it now or after discussing? Okay, so remember we drew in the figure in this picture of H1 and lambda 8 eigenvalues, and in that case we had perfect so 60 degrees here, and then minuses of them. Okay. So this was alpha 1 root, this was alpha 2, alpha 3, and minus alpha 1, minus alpha 3, minus alpha 2. Okay. Okay, it is convenient because there is always, for every root we have a negative root, right? So it is convenient to group them in terms of what we call positive roots and negative roots. It turns out to be convenient. So the way you do it, and we will discuss it in much more generality next week when we discuss generally algebra. No? We will give a more precise definitions of all these statements. But at the moment, I just want to give you some kind of intuitive understanding of this. So we define positive roots in the following way. Now, what you do is, in this figure, draw some line, okay, which does not intersect, passing from the origin, which does not intersect any of the roots. Okay? Of course, there are infinite number of ways you can draw the lines. So, for example, I can draw this line here. Okay? This line clearly does not intersect any of the roots. Now, and then you just declare that everything lying on one side are the positive roots, and then everything, by definition, everything lying on the other side is the negative roots. Okay? So this is the way to define positive roots. Notion of positive roots. Okay. I could have, of course, chosen something else. This line. In that case, I would call the positive root. For example, I could call these three as a positive roots, or I could call these three as a positive roots. Doesn't matter. It is just renaming the things. It's not. There's no fundamental difference. Okay. But since I have been using this alpha 1, alpha 2, alpha 3, I'm implicitly kind of calling them as positive roots. I will consider a line like this, and then these three guys are positive roots. So this side is all positive roots, and here is all negative roots. Now the other thing is, now let's focus on the positive roots. one thing you notice, this way of defining it, when you take positive roots and look at the commutation relations between, say, x alpha I, x alpha j, they are both are positive. Huh? So it's one of these three. Those are one of these three. Huh? Then the result, whatever you get, is again, of course, it could be 0, right? But if it is not 0, it is again another root, positive root. You see, taking the commutation relation of two positive roots, I mean positive root the elements x alpha 1. So for example, x alpha 1 with x alpha 2 will be x alpha 3. It will never give you a negative. And that is not hard to see, hard to understand, because we already saw, and this is very important relation, which you have to, that if I look at some root x alpha and x beta, the commutator of this will be some x gamma, I mean proportional to some number times x gamma, okay, where gamma is alpha plus beta, right? This was a very important relation, and that relation was very easy to obtain. All you need to do was just to look at the commutation relation of x with this guy, whatever this guy is. Huh? So x alpha, x beta, this, okay. And then we use the Jacobi identity. Jacobi identity is, as I told you, is same as like taking derivative. I mean, you can use Leibniz rule. That's what, when I say derivative, I mean you can use Leibniz rule. Leibniz rule, you remember, right? I mean, d by dx of, say, f1 of x and f2x is the same as, there are two terms, so d by df1 by dx times f2x plus f1x d by dx f2x, right? So it's a Leibniz rule. Term by term you take a apply derivative. Okay? The same thing you can do here, but you have to of course remember that these are they're not abelian. They don't commute. So you have to keep that position in the same place. You can't change the position. Unlike here, you could these are functions, you could just put it there. F2 you could put it there. But it doesn't matter because it's commutes, right? Functions commute each other. So, but here you have to keep track of that. So therefore, keeping track of that, so I said the commutator is like taking derivative, right? So I take this, I think of this as a derivative. Then I have to apply here and there, two terms, right? So when I apply here, I will get, so is this object, so derivative acting on x alpha, but what is a derivative? According to our definition, derivative is the commutator, right? So it is same as taking commutator, and then you have x beta, plus the other term, which is x alpha, and then I apply the derivative on x beta, but the derivative is the same as taking the commutator. So this is a very easy way to remember. This is the same as Jacobi identity. But then you use the fact that these are already eigenstates, and the eigenvalue is alpha h. Oh, I didn't put it. Okay. Yeah. Okay. So the eigenvalue of this is alpha h, and then of course what is left over is x alpha x beta. This I repeat again because this is really the very important relation. And here you get x alpha, and again this is the eigenstate with the eigenvalue h beta. I'm sorry, beta h. Again, it's a number, I take it out. Beta h, x beta. Right? So you see that this is again an eigenstate with alpha h plus beta h. That's how you conclude. See? Okay? But now you see that whatever the result of this is, what you get here, alpha k, should be the sum of these two vectors, right? Now, if both these vectors are on this side of this line, the sum of them also is going to be there. It will never give you a negative root. Okay? So it's just that, the simple fact like that. So it's going to be always positive. Okay? And similarly, if you take the commutation relation of two negative roots, it's always going to be negative. Okay? Of course, if you take the commutation relation between a negative and a positive, then you cannot say anything about it. It could be, positive or negative. Then you cannot say anything about it. So this is one thing. Secondly, if you look at this, now let's focus on this positive roots. Okay. Now I want to. So we want to see how much, I mean, what is the information contained here? I mean, say I want to look at, I mean, various properties. I mean, how these X alphas commute, how this X alpha 1, alpha, X alpha 2, X alpha 3, etc. commute with other elements, or how they act on some representation space, etc. Right? The point is that, since if I look at the commutation X alpha 1 in specific thing, X alpha 1, X alpha 2 is X alpha 3. Right? That means if I know how each of these guys act on some vector space, then I already have that information. You see? So it's like X alpha 3 can be constructed out of this. Once I know fully, say in some vector space, some representation, this is represented by some matrix, that is represented by some matrix, and I found these matrices. Okay? Then this I can just obtain for free by just taking the commutator. Okay? So somehow it is enough to look at this guy and this guy. Okay? Of course, I'm talking about with respect to this particular choice of positive roots. Suppose I had chosen some other positive roots, let's say here. Okay? So then the positive roots are these guys. In this case, this will be the commutator of these two. Right? So I can just take this as the, I mean, if I know this information, then I can construct that. Right? Now, these guys, so for a given choice, you look at these roots, which kind of have independent information. Okay? Then I can construct this guy. So we call this as simple roots. This again a terminology. So in this particular choice, I'm choosing always this guy now. This, so this is positive roots. In this case, we call X alpha 1. So alpha 1 and alpha 2, we call simple roots. These are called simple roots. Simple in the sense that because other things you can construct from there. So we will discuss all this in much more detail. I mean, in the SU3, it's not so crucial to introduce these concepts because everything is pretty explicit. But when you go to more general Lie algebras, it is useful. I mean, these concepts are very useful. For the time being, I'm just kind of saying. So we introduced two notions: positive roots and simple roots. Okay.
In the definition for them is there is no way to write them as combinations of letters.
Exactly, other positive roots. Yeah. So basically, the definition is that. So here, alpha 3 is the same sum of alpha 1 plus alpha 2. So what you do is that you look at so all the roots which cannot be written as linear combination of positive roots with positive integers. Okay.
We are allowed only to make linear combinations and Lie brackets, right? Are we also allowed to just multiply two matrices?
No, not in the that will not be part of the algebra. That will not be. Yeah.
Either by linear combination or by creating brackets.
Brackets. I mean, of course, yeah. If you are already in a representation, then you can multiply those matrices. But the result is not going to be the algebra. It will not be an element of the algebra. I mean, take an example, SU2, sigma 3, right? If I take sigma 3 times sigma 3, it is identity, it is out of the algebra. Right? Yeah, so the more kind of invariant way of defining this is that the simple roots are those positive roots which cannot be expressed as linear combination of other positive roots with always coefficients positive. Okay? I mean, if you put some negative coefficients, of course you can make, right? For example, I mean, alpha 3 minus alpha 1 is alpha 2. But I'm not allowed to put minus, negative signs. So that's there's a way to define simple roots in a more precise way, which, by the way, is equivalent to this. I mean, which is just equivalent to this what I said. That I mean, if anything, so let's say if any root alpha can be expressed as sums of some, I don't know, say ni alpha I, right? Ni are some integers, positive, not negative. I mean, non-negative. It could be 0. Some of them could be 0, but important thing is non-negative. If you can do that, then you see this alpha, I can write it as multiple commutators of this x alpha I, huh? in some various combinations. So therefore, you can get all the information about this root if you knew the information about this is the idea. Okay, so the simple roots and positive roots. Now that a remarkable fact is that number of simple roots is given by the dimension of this root space. In the SU3 case, as you see, there are only two. For a given choice of positive roots, there are only two simple roots. Okay? A number. So the number of simple roots is this equal to the dimension of the Cartan subalgebra which is of course also the dimension of the dual space, right? Remember, the alphas are living in the dual space of this. Okay? So this is an important fact. This again is a general feature for the class of Lie algebras we'll be talking about. The class of Lie algebra will be what we call semi-simple Lie algebras. But I will come to the definition of semi-simple next week. What is simple, what is semi-simple, etc. But these are all the SUNs. SUNs are all actually simple algebras in that definition. SUN, all the SUNs and SONs. SONs are also simple. SON for n greater than 4 are all simple algebras and so on. Okay, these are some facts to keep in mind. Okay, now let's go to the fundamental representation. Okay, one more thing I wanted to say. So now you see, you can ask the question, given this adjoint representation, this has all the information about the adjoint representation, right? These are the non-zero roots, and then of course there are two Cartan generators. That's altogether there are 8 generators, right? Now if you look at this, then you ask the question, which state is annihilated by both the simple roots? When I say simple root, it's a abuse of terminology. What I mean, the x alphas. No? So in our case, alpha 1 and alpha 2 are simple roots. So the generators corresponding to them, x alpha 1 and x alpha 2. These are the generators which correspond to the simple roots. So look at all these states and ask the question, which of these states is annihilated by both x alpha 1 and x alpha 2? It is this one, right? No. This is called the highest weight state. Okay? Just like in the SU2 case, we had the highest weight spin, the J. M equal to J was the highest weight state, right? M is the J3 quantum number and J is the spin J representation. So here the analog of that is, now since you have, not just one raising operator, there are several raising operators. So you have to have a definition of highest weight. Okay? And this is what the definition of highest weight. This guy, for the adjoint representation, this x alpha 3 is the highest weight vector. Because both x alpha 1 annihilates it. When you take the commutator, x alpha 1 and x alpha 3 is 0, and similarly x alpha 2 with x alpha 3 is 0.
Do these positive roots constitute a representation in themselves?
No, that will not be. Because, if you take any of this, basically what you're looking at, this is just a way of, you still have the full algebra, right? So you have, what you do is that you look at the SU2 subalgebra of this and SU2 subalgebra coming from there. So this one will be x alpha 1, x minus alpha 1, and the H1.
Yeah, to slice it into SU2s, like we did.
That's what it is.
Yeah. But maybe this is another kind of algebra which we talk about right now, is the representation of that kind of.
Yeah, okay. That would be, this would be, you can restrict to that. So of course this will be an algebra, right? X alpha.
The positive roots constitute the algebra? So
no, it is not a simple algebra. It is if you write a metric, it's all degenerate.
But at least we can talk about highest state of.
Yeah, but the reason for highest weight, even for the SU2, when we talked about spin J, what we said is it's annihilated by the raising operator, right? But then you apply the lowering operator, construct all the other states. So it's the same way here. If you start with this, then the claim is that you can get all the other states just by applying these two SU2s. Right? So anyway, the raising operators annihilate that. So that's the highest weight. Now you start applying the lowering operators, and you construct all the other states. So, for example, here we know that with respect to this SU2, this is a doublet, spin half, right? So when you apply a lowering operator, this root will go to that, right? It's just adding the vectors, so it's just parallel lines. No? So this will go there under the action of x minus alpha 1, and this will go there under the action of x minus alpha 2, because minus alpha 2 is like going down there. Okay? Then again you arrive here and you look at, then of course you can construct from here, this is a joint representation of this algebra, SU2 algebra, so you get that and that. This is spin 1 from this SU2 point of view. And for this one is spin 1 from this point of view, so you get that and that. Okay? And then again apply a lowering operator here, you get that. So you construct all these states. In this process, you see that unlike the SU2, where the multiplicity at each level was only 1, right? When you bring the lowering operator, you'll get just one state. There are no two states with the same n quantum number, right? In a given irreducible representation. Here it is not the case, which you can already see here. You see, let's look at this here. This is the zero root, which means Cartan subalgebra. Cartan subalgebra is two-dimensional. So multiplicity of the states here is 2. Okay? Why is it 2? Because to arrive here, there are two ways of arriving here. You see, one way I can apply this lowering operator, then I apply this lowering operator. Okay? There's another way of arriving here. I can apply x minus alpha 2 first, then I apply x minus alpha 1. There are two ways of arriving here, and one can show, it requires a little bit of calculation, that these two states are linearly independent. Okay? These are not proportional to each other. They are linearly independent. And therefore you come to a conclusion there are two states.
Can we count, sorry for my
Yeah?
Counting the ways you can arrive at a point, will always give the Cartan subalgebra dimension?
No. Yeah, I mean, okay. Yeah, sure. No, I thought you were asking a different question. Let me just tell you what I thought you were asking. I mean, this is not always, it's not such a simple counting. No? For example, let's say here, to arrive here, how many ways I can arrive? I can, starting from here. And I'm allowed to only use a lowering operator. This is the rule, I'm only allowed to use a lowering operator. So I can come here, 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 right? Or I can come this way, this way, this way. So it seems there are two ways, but the multiplicity is not 2, it's 1. Okay?
Why we didn't use minus alpha 3?
No, because as we said, we are not going to use this thing, because anyway, the information about x alpha 3, this SU2 subalgebra, is contained or completely here. Because x alpha 3 is nothing else but the commutator of x alpha 1 and x alpha 2.
You can do all alpha 3 operations with alpha 1 and alpha 2.
Exactly, that's the point. You don't learn anything new by using alpha 3, because that information is already here, right? And same thing with the x lowering operator, x minus alpha 3 is again proportional. I mean, these are some numbers. I know. X minus alpha 1, x minus alpha 2. Okay. So again, applying lowering operator here is equivalent to applying lowering operators of these two, right? In two different orders. So there's no new information. So that's why. So you just apply this negatives of the simple roots, and see how many ways you can arrive here. It is not guaranteed that just because you are counting, say there are 10 ways of arriving at some point, it doesn't mean that there are 10 states necessarily. Okay? You have to check if the states are linearly independent, and that requires a little calculation. It's not immediate. So as a counter example, I told you here, there are 2 ways of arriving, like that or like that. But this cannot be 2, Why it cannot be 2? Because this state is only 1. There's only one way of arriving here from the highest weight, right? And by this while reflection symmetry, if there is one state here, there can only be one state here. Okay? Or another way to say is that under this SU2 representation, it's not possible that there are 2 states here and one state there, right? So there are ways of, I mean, it requires a bit more work to compute the multiplicities. But at least you can see all the possible routes which appear.
And the multiplicities, in that case, gives the Cartan-Sabah algebra I mentioned.
That's what it is. Because there are 2 linear independent objects which have zero eigenvalue, right? And those are the H1 and H2, or combinations of H1 and H2. Okay, so highest weight, you see the notion of highest weight is a bit more complicated than SU2. It's not surprising because now you have several SU2, so you have to, I mean, it's a good thing that we don't need to use all the 3 SU2s, right? It's enough to use just the 2. And that is just given by the simple roots, and the simple roots is the number of simple roots is the same as the Cartan, dimension of the Cartan subalgebra. Okay. So if you go to SU4, there will be 3. Simple roots will be 3, and you have to give the highest weight to be defined by that state which is annihilated by all the 3, and so on. It becomes more and more complicated. Okay, so let's now look at the fundamental representation. So what are the eigenvalues? Fundamental representation, we have to do nothing, because already we have chosen the Cartan generators which are already diagonal 3 by 3 matrices, right? So we have to do nothing. So let's write down. Remember H1, H2, H3. H1 was sorry, this one. We chose this guy. And H2 was 0, 1, minus 1, 0, 0, 0. And so fundamental representation is 3-dimensional representation. So think of these guys as acting on a 3-column vector. X, Y, X1, X2, X3. Right? Some 3-column vector. And you want to ask to find out what are the eigenstates of these 2 operators. Right? This is already, I mean, sort of, maybe I should use the notation capital H. Because H1, etc., H1, H2, etc., I'm thinking of as abstract Lie algebra elements. But now there is explicit 3 by 3 matrices here. No? So this is a representation. And similarly, capital H2. Eigenvalues are very clear. I mean, I have 3 eigenstates. 1, 0, 0, because these are all diagonal, so I don't need to, and another one 0, 1, 0, and another one 0, 0, 1, right? Three independent guys. And then what are the eigenvalues? Well, if I apply H1 on this, I will get 1, right? In this notation, in this notation, I'm writing the eigenvalues of the 2 operators, H1 and H2. So now, with respect to H1, you just multiply this. You see this number 1 times 1. So you get 1. Whereas if you multiply H2, it's all 0, right? Because, I mean, you see, multiplying that gives you 0, right? I mean, H2 times this state, right? This vector gives you 0. Now, about this one, what is it? H1, if you multiply, you see this picks up a minus 1, okay? And when you apply H2 on that, it picks up a plus 1. These are the eigenvalues. And finally, here, you get 0, 0, minus 1. Right.
No, 0, minus 1.
0, 0, minus 1, yeah. This is minus 1.
Yeah, but
just 0 minus 1.
Just
Yeah. 0 minus 1. Okay. 0 minus 1. So now, this was H1, H2. One can, I mean, if you want to draw it in the same picture, it is better to go to the, because here I'm plotting H1 and lambda 8, right? So we can convert this into H1 and I don't know, lambda 8. Lambda 8, what was it? 1 over root 3. I always forget. Lambda 8 was 1 over root 3, 2h1.
Plus H2.
Huh?
2H2.
2h2 plus h1, is it? 2h2 plus h1. Good. So let's see. So if I plot that, so if I write down this number, okay, h1 is 1, and then 1 over root 3, h2 is 0, so it's just 1 over root 3, right? H1. And here you get minus 1, and then 2h2, so 2 minus 1, 1, 1 over root 3. And then here we get 2, so h1 is 0, so it's just minus 2 over root 3. 0 and minus 2 over root 3. These eigenvalues, h1 and lambda. So let's plot that. Unfortunately, there are too many things here. So let me just erase it and plot it again, because there are too many lines, you can't really see anything. Yeah. Okay. So here I have this here. So the roots, remember, was like here. So this was 2, right? And this is 1, 2, 1, 2. So the one of them was like that here. Other one was here. So this is minus 1, minus 2. So this was maybe it should be a bit more longer. Yeah. So we call this alpha 1, alpha 2, alpha 3, and then the negatives of that. This is minus 1 here. So minus alpha 2, minus alpha 3, minus alpha 1. Okay. Now let's see plot it here. So this one is 1 over root 3. Okay. So this was remember 2, right? I mean that was a 2 for the h1. So that was 2. So this is the half. So you come here in the half and 1 over root 3. Okay. So that's going to be well, what is so if I draw the angle, this is what tan of theta. So this angle is theta, right? Tan of theta is 1 over root 3. When will that be? Tan of theta 30 degrees, I think. 30 degrees is correct, right? Because sine 30 divided by cos 30, right? Sine 30 is 1/2. 1/2, and cos 30 is root 3 by 2. So it's 1 over root 3, right? So we are, so you see it's exactly bisecting this angle. This was 60 degrees, this one before for the roots, and this is like drawing this. And in fact, you can see that if I had drawn a parallelogram here, parallelogram like this, and draw the diagonal, which will of course bisect this, and take this diagonal and divide it into 3 equal parts. So this one is this. Let me call it W1. Okay? I don't know, do we use some particular notation for this? For the rates? Okay, anyway, let me just use this. Oh, anyway, let me just call this as a W1. This one is W2. So this is the first state, second eigenstate, and these are the 3. These are called weights. Okay? Just like alphas are called roots, these are called weights. Okay. So this is W1. Okay. W2 is just, you see 1 became minus 1, but that part is the same. So it's just a reflection in this, yeah? So it will be like here, somewhere here. And W3 is 0 along this axis and minus 2 over root 3. Okay. So it will be something like here. Minus 2 over root 3 is probably somewhere here. So this is minus 2 over root 3. So this is W1, W2, and W3. Note that the lengths, I hope is correct, the lengths of all of them are equal, right? If you take just 1 plus 1 over 3, length square is 4/3, 1 plus 1 over 3, 4/3, and this is 4/3. Again. So length square. Because let's take the square of this plus square of that, right? To get the length square. Those are all equal. So these lengths are all equal. So this length is same as that length. Same as that. That's because we are plotting the lambda 8. If you are plotted with h1, h2, it will not be any such thing. Okay. Now this is very, again, a beautiful diagram. It's a kind of equilateral triangle. And these are the things here. Right. Now in this representation, again, choosing our simple roots, alpha 1 and alpha 2, can anyone say which one is the highest weight? The simple roots are alpha 1 and alpha 2. So of these three states, which one will be the highest weight?
2.
No, highest weight, which is annihilated by both alpha 1 and alpha 2. Annihilated. Is this one, you see, because nothing. If I apply x alpha 1 on that, I'm going to get something here, right? But there's no such thing in this representation. Similarly, if I apply this here, starting from here, I will get something here, right? Again, it's not there. So this is the highest weight of this representation.
We know the applying them also causes the additive result.
Yeah. It'll be always the same. I mean, that's easy to say again. Yeah, in fact, that's a good point. I didn't prove that. I just assumed. But yeah, it's a good point. So let's say, if I apply now, in any representation, this is not just a fundamental representation, any representation. Suppose I apply some Rx alpha on some state, how shall I call it? Some state which has weight W. So I'll just use this notation. So by this, I mean, for the fundamental representation, these are the weights. If you take some other representation, it will be corresponding weights. Again, you decompose those states in terms of eigenstates of H1 and H2 or H1 and lambda 8. And that collection of numbers is this W. That specifies the state, right? So if I apply that, the claim is that you will get something which is of the form W plus alpha. And let's see how. Of course, the coefficient could be 0. I mean, this could be 0, but if at all it's not 0, it's going to be something with the eigenvalue W plus alpha. Okay. How do you see that? Let's apply R of any H. H is the Cartan generators. Apply on that state. Then our famous trick of writing this as a commutator by pushing. You want to push it through inside, right? So this is the same as a commutator. RH, Rx alpha, acting on W, plus the other order, Rx alpha, RH, W. Okay. Now this one, RH acting on W by definition was W, right? RH, in fact, that's what we did, the eigenstate, this is our eigenstate. RH acting on W is WH, W, right? That was the definition of the eigenstate. So this guy just gives me WH, W of H acting on the state. That's a number, take it out. Then you get back Rx alpha times W, right? But multiplied by WH. This, on the other hand, is alpha H times Rx alpha. Right? This is clear, right? Because we are looking at the commutators of R, of H, RH, Rx alpha. Commutator. But this is supposed to preserve the Lie algebra structure. So this is the same as R of the commutator Hx alpha. Right? But Hx alpha is the eigenstate. So this just gives me R of alpha H x alpha. Right? Alpha H is a number and representation is always a linear map. So this is the same as alpha H R x alpha. Okay. So this just gives me again alpha H times Rx alpha acting on W, and this gives me WH times the same state. So it becomes alpha plus W. So it doesn't. So this state is again an eigenstate of H of the Cartan subalgebra, but with the eigenvalues which are added up. W and the eigenvalue of that. So this is a completely general result. For any representation, this is true. Okay, so that's why. So this is the highest weight, because nothing, you don't go there, you don't go there. Right? This is the highest weight. But then you apply the, and now you see, this guy is is a doublet of this SU2 subalgebra, right? Because you see this, by looking at this number already you can see. This number is, remember, because now we are using, we don't have we have not divided by half. Remember, to write this in SU2, in order to get integer, we had to, how shall I say, we divided 1/2 of sigma 3, right? Here we are not dividing 1/2 of sigma 3. We are just taking H1 was just the sigma 3 part in the top 2 by 2 block. We didn't divide by 2. So all the numbers will be multiplied by 2. Okay? So before in the SU2 language, what I was calling M, here it will appear as 2M, right? Because I didn't divide by 2. So it will be 2M. So in order to see which spin it is, you just divide by 2 to get back. So this is spin half. Already, this is the highest weight state. He said this is the highest weight state. Just by looking at this number, you can see that it is the, okay. So from here, you, this number was in the, if you want to look at, this is already in the lambda 8 language. Okay, so don't take the second number seriously. Okay, lambda 8 was not one of the J3 component of one of the SU2 subalgebra. It was not like that. Huh? We had H1, H2, that was a combination, or H1 plus H2. These were the combinations. Yeah, you can go up here. You can go up here. If you look at this, you can immediately see what spins are there. So this tells me it is spin half with respect to the SU2, first SU2 algebra, this SU2 subalgebra, and spin 0 with respect to other SU2 subalgebra. That means it's a singlet of this SU2 subalgebra. Okay, and in fact, although this picture is not very clear, but you can see that this angle is exactly 90 degrees, because this was 120 and that was 30, so this is really 90 degrees. So it's okay. So this is a singlet. This singlet of that and the doublet of this. So doublet, of course, means that I'll have, when I apply a lowering operator, I will come here, but after that it will not go further because it's only spin half, only doublet, 2 states here. Okay. Yeah.
I didn't understand why W1 was the highest weight.
W1 is?
Highest weight, I didn't understand.
W1 is, why is W high? Okay, because he said, how the highest weight is defined? It should be annihilated by both of these guys, the simple roots. So in other words, R of X alpha 1 acting on the highest weight state, let me call it WH. WH for the highest weight equal to 0. And similarly, R X alpha 2 acting on WH must be 0. This is a definition of the highest weight. For SU2, for SU3. Because there are only 2 simple roots. Now, we also saw that when these guys act on it, the resulting state will have a eigenvalue H plus alpha 1. Right? Now look at here, W1 has this weight. Now, if I look at, if I apply alpha 1, the resulting state must have an eigenvalue here, right? This vector plus that vector will be this, no? But this was not there in our, we already constructed all the eigenstates. This was a list of all the eigenvalues. This didn't exist. So necessarily it must be 0 here. Right? If it was not 0, then it should have gone there. But that state doesn't exist. So, and the same thing with this, if you apply that, you should end up somewhere here. But there is no such state here. So therefore this is the highest weight. But then to construct the full representation, now you start applying the lowering operators. Lowering operators, so I apply X minus alpha 1. So I'm going to go here. Okay. If you apply x minus alpha 2, it doesn't go anywhere. This is actually a singlet of this SU2. But once it comes here, this state is not a singlet of this one. So again, repeat. Since I know this is spin half, doublet, with respect to this SU2, you apply one lowering operator, you come here, right? If you apply one more lowering operator, it gives you 0. So it stops here. This chain stops here. But now I apply the lowering operator of x minus alpha 2 here. Then I'm going to come here. You see, you just if you draw precisely with all the correct angles and so on, you will find that when you subtract this vector, you come here. Okay? This way you generate all the three states. So the way the picture is, these two states form an SU2, doublet of this SU2. These two states form a doublet of this SU2. Okay? And this guy is a singlet of that SU2, because this one doesn't go anywhere up on the action of this. Same thing, if you look at, let's say these two states are a doublet of this SU2. Okay? We never use this alpha 3, but of course there's also an SU2 subalgebra there, right? If you look at this SU2 subalgebra, these two form a doublet, because this is moved there and that's moved there, right? But this is a singlet of that. Huh? So you see, this is a very nice structure. This triplet splits like this. Take any of the SU2 subalgebras, or the three SU2 subalgebras. Two of the states, 2 out of the 3 form a doublet, and the other one is a singlet. And which 2 depends on which SU2 you look at. Yeah? So that's the picture. But notice that there's something strange about this, right? This doesn't satisfy our mirror symmetry things, right? Mirror symmetry is not the right word to use, because mirror symmetry nowadays is used for something completely different. But this is reflection symmetry here. Reflection, because we said, well, actually no, this has a reflection symmetry. Sorry, this is a reflection symmetry, you can see. Because the reflections are with respect to the perpendicular plane, right? So if you take the perpendicular here, this picture is symmetric. If you take the perpendicular of that, which is here, this is again symmetric. Yeah, so reflection symmetry is fine. But there's something else which is strange compared to a joint representation, that for a joint representation, for every eigenvalue, there was a negative eigenvalue, right? But here is not the picture, is not happening. And this brings us to, you had some question?
Related to this, basically the same question, but in a joint representation, we solved the eigenvalue equation and we obtained 6 solutions. We have now just 3.
Yeah.
But we are restricted to 3 because we use 3 by 3 matrices.
Yeah,
so we cannot find any other eigenvectors.
Yeah. The 3-dimensional representation, right? Or another way to say that, of course, we happen to know this because this was a defining representation. No? Now, this was a defining, so we already know there's a 3 by 3 representation. But suppose I want to construct a 6 by 6 representation. Okay, I don't know anything about it, right? So how will I construct it? You just specify the highest weight and start constructing all the states.
Well, is it like the defining representation is smaller than the adjoint or 6-dimensional representation? Defining representation is not enough to see the whole picture in this case?
Yeah. No, sorry. At the moment we have this, as I said, for any Lie algebra, there are two representations which come for free. One is a defining representation, which is SU3 cases 3 by 3, and other is a joint representation. These two things come for free. But just like in SU2, the defining representation is 2 by 2, so it's a spin doublet, and the joint was a spin 1, right? But what about our other spin j, right? So for that, what did we do? We went to the highest weight, we started with the highest weight, and then constructed all the remaining states, right? So here also, I can construct the highest weight state, right? Highest weight state, again, you see highest weight state is just specified by giving 2 integers, 2 positive integers. non-negative integers. Just like for the SU2, because we have multiplied by 2. So what we are specifying is 2j, right? So these numbers will be 2j, not j. Because j, remember, could be half integer or integer. But 2j is always going to be an integer. So SU2 representation in this normalization, where for h you just use sigma 3. Those will be just any positive integers, any non-negative integers. For every such integer, there is a representation, irreducible representation. Now here, the analog will be just specify 2 integers, n and m, 2 integers. I don't know, n1 and let's call it j1. No, let's call it n1 and n2. 2 integers, which are non-negative. It could be 0. Some of them could be 0. No? But the important thing is nothing is negative. Give me any such integer, you can construct an irreducible representation for SU3.
But in H1, H2 basis.
Basis is, of course, your choice. I mean, yeah, in the H1, this is an H1, H2 basis. Sure. It is in this way, in this language. Because not here. Here is 1 over root 3 and so on. Yeah. In the H1, H2 basis, which are, which is,
yeah. So it is not evident in this picture because as we create new states, either we go in alpha 1 or alpha 2 direction, and the steps are not integer if you look at this picture. But if you would look at the H1, H2 picture, but we are sure that the steps in both N1 and N2 are +1 or +2, +2. I mean, every possible representation must be integers, we said. But it is because of the creation operator acts on the eigenvalues like adding them +1.
Yeah, but I mean, because we already know, I mean, that's the point, but from what we have learned from SU2. From SU2, we know that any representation of this SU2 can have only integer eigenvalue. H corresponding H will have only, H meaning corresponding Kartam of this SU2, will have only integer eigenvalues. No? And the highest weight will have positive, I mean non-negative integer eigenvalues. You specify that, and then of course it will follow into the steps of, the lowering operator will just give you, in this normalization, it will bring you 2 steps down, right? Instead of 1 integer. So that is guaranteed. I mean, anything else will be inconsistent. Because we already know that we have completely classified all the finite dimensional representations, right? And we are here looking for a finite dimensional representations. So if it's a finite dimensional representation, if there's no other alternative, that's all you have. And that has to be true for every SU2 which is sitting inside. Right? In this particular case, as we said, this SU2 is superfluous because this doesn't have any new information. I have all the information coming from considering this SU2 and that SU2. So you just specify the 2 integers corresponding to these two SU2s. The highest weight integer, highest weight spins, that's what I'm basically saying. The highest weight spin of this and the highest weight spin of that. You specify, and that completely uniquely fixes the representation, irreducible representation.
But still we know that after adding up all these rows, we always end up at an integer.
That has to be right, because the steps, I mean, all these things, what are we doing? We are applying the lowering operators, right? When you apply the lowering operators, I erase that. Yeah, here, you see, these are the lowering operators eigenvalues. These are always integers, right? So that is guaranteed, right? Because this is additive. I mean, this becomes W plus alpha or W minus alpha, depending on whether you put. So it's always additive like that. Okay, so yeah, now so
for then not every integer is possible because sometimes we have to like we can combine them to make up any n1 and n2, right? This must be true.
No, n1 and n2 you specify. Just like you say spin j. Spin j represents.
But for j we could choose integer or half integers, any.
And in this normalization is all integers, because we have, I mean, remember that, I mean, the SU2 we were using half sigma 3, right, as H. So for this, of course, it was, I mean, half integers or integers, because of the fact that I have a half here. But in this SU3 discussion, we didn't put that half there. So in other words, I have to multiply. So what we were calling for the SU2, we were calling the H to be half sigma 3, right? But here in this discussion, we are calling H, so multiply by 2. This is 2 times H SU2. I mean, I mean by this is that normalization I used for SU2. Now I'm using twice that because I'm just using sigma 3. Remember H1 was just that, right? 1 minus 1, the sigma 3 part. If you look at this 2 by 2 block, it was a sigma 3, not half sigma 3. So for this reason, the eigenvalues of these guys will always be integer. So yeah, you never get half integers. I mean, we could have also used the same normalization as you, but then we have to worry about all these half integers floating around. So it's much more convenient to use this normalization, where everything is integer. Of course, I mean, half or even or integer just means that whether it's odd number or even number there. That's all. So this was an odd number. That's why we said this is a spin half representation, right? Spin 1. If it was 2, then it would be spin 1 representation. It's just a terminology. Sorry. Okay. So now going back to this thing, I mean, there's one crucial difference between this fundamental representation and the adjoint representation. The adjoint representation, for any root, there was also a negative root, right? Here it is not the case. This, I mean, the negative of that would be out there. This triangle will get inverted, right? But that is not, you don't find that. And that is where the complex conjugate representation appears. So let's describe the complex conjugate representation. So use this here. So what we need to do is the complex conjugate. Actually, this. I think I don't need this here. Okay. So the complex conjugate representation is, so if I give you some representation of R of X, then there's a map to go to the complex conjugate. It was simply minus Rx bar, right? And we saw that this satisfies the algebra, right? So it's also a representation. But if you do that, so now what will happen to, let's look at the R of H1 or H2. Right? That's going to be minus R bar of H, but RH, the H that we have chosen, they're all real. Okay, so which is the same as minus. Now, so that means in this, whatever the eigenvalues were there in the original representation, in the complex conjugate representation, your eigenvalues will all become minus of it. Yeah? So that's the complex conjugate representation. So this is what, this is again a difference between SU2 and SU3. You see, in SU2, every representation was self-conjugate. The complex conjugate representation gave you back the same thing. It's just a relabeling the basis, nothing. They were equivalent. Here it is not the case, because now in the complex conjugate representation, so this eigenvalue will go over to that, minus. Similarly, this will go over here. This will go over there, right? Because of this. You see that? So what does it mean? So if on some state RH had this eigenvalue WH, then this guy, then in the complex conjugate representation minus RH, it is simply minus WH. So the weights will just go in the become negative. Put a minus sign so everything goes back.
Isn't the same but shifted or?
Yeah, it is. It's of course again an equilateral triangle, but it's just kind of it's upside down. So one of them is like this here. The complex conjugate representation is here.
So
Okay.
it's the same.
Yeah, the same as rotation. Okay. So this is a nice star shape, right?
Starting to understand.
Sorry?
No, that I am starting to understand.
Try to understand. Yeah. I mean, this is the W3, and let's say this is the I don't know. Let's call it W bar 3. This is W bar 1. Just to say that this is in the complex conjugate representation. These are the reads. Okay. So so that is the crucial thing. Only for SU2 you have this. There are some other algebras also, but at least we have seen SU2. Every representation was self-conjugate. No? Complex conjugation gave you back the same representation. Here it is not the case. Here it happens that some of the representations are actually invariant under a complex conjugation, like a joint representation, because in a joint representation, the roots, for every root there was already a negative root. So the complex conjugation doesn't do anything. It will take you this to that, but they were all already existed. So it's just changing the basis. You just relabel the basis, you get back the original thing. So they are equivalent. But here it is not, because eigenvalues are different, so there's no reordering will do anything. No reordering of the choice of the basis in this three-dimensional space. It will not bring you that. So that is that's the thing. Okay. Eigenvalues will not change under the similarity transformation. The set of eigenvalues that are there will not change. You see that point because after all, if I give you some matrix M and I want to ask the question, what are the eigenvalues of this matrix, right? The easiest way is to just compute this determinant of M minus lambda times the identity matrix, right? And look at all the possible roots. If this is n by n, then this is also n by n identity matrix. So this will be nth order polynomial, or in lambda when you open the determinant, and when you use this, there will be n solutions, right? So this will be nth order polynomial, in lambda, and therefore there should exist n solutions. Of course, some of them could be degenerate, but there will be n solutions, counting the degeneracy, taking into account degeneracy. So n solutions. But now, if you do a similarity transformation, so the change of basis, remember, corresponding to similarity transformation. So instead of M, you now look at the similarity, transform the M, and ask what is the determinant of this? What are the eigenvalues of this? And that you see, again, let's put this, so let's call it lambda prime, the new eigenvalues of this identity. But then identity itself is S inverse S, right? And then I can rewrite this as determinant of S inverse n minus lambda times identity, lambda prime times identity times S. Okay. But then determinant is a product of determinants. Determinant of S inverse will cancel determinant of S, and you're just left with the same thing. So you'll get the same polynomial. So you'll have the same eigenvalues. Eigenvalues don't change under similarity transformation. Here eigenvalues changed. So you are already guaranteed that this is no similarity transformation will bring you down. Okay. So they are inequivalent representations.
In the joint one?
In the joint?
There is a.
In the joint one, yeah, because so the crucial thing is to check if the roots for every weight there is a negative weight or not in the same representation. If it is, then they are equivalent. But if it is not, then they're different. I mean, the complex conjugate representation will be different from the original one. Okay. Let's see what I can say. Okay, so okay. Now, if there are no questions, let me just start. Let me say briefly some things about the other representations. So just let's take some example. So I told you that you specify these integers, non-negative integers, and you are guaranteed to have a representation, irreducible representation. So just like, so that's the point. So irreducible representation is labeled by 2 integers, okay? Whereas in SU2 it was labeled by just one integer, 2j. In my normalization is 2j, so that it's always an integer. Now here it is now 2 integers, non-negative integers. If you go to SU3, SU4, it will be 3 integers, and so on. So that's how the whole process will develop. So now let's just take some simple cases. So this one, we already know, this fundamental representation, the 3 represent, is usually called, just a notation, the fundamental representation is denoted by 3, because in SU3, because it's a 3-dimensional representation. The complex conjugate is also 3-dimensional, right? But you want to distinguish them, right? So you will use some notation, and the complex conjugate representation is denoted by 3 bar. The bar is clearly, I mean, just telling you that it's a complex conjugate of that. That's it. So this was the kind of, the fundamental representations, and then we also have a representation 8, which is the joint representation. Okay. Now, in this notation, what are these representations? This 3 was 1, 0. This was the highest weight, right? This is the H1 eigenvalue, H2 eigenvalue. Right? So this was, the highest weight here was 1, 0. Here, it is, let's see which one it is in this notation. Sorry?
0, 1.
It will be 0, 1, exactly. Yeah, because it will be this W3 bar. W3 bar is annihilated by both this and that, right? So is this one, and it is 0, 1. So this will be 0, 1. And this 8 is 1, 1 in the notation, right? Is this guy, alpha 2 is 1. So let's see, let's take another example. Let's see what else we can do. I mean, the simplest thing could be, for example, 2, 0. Okay. Let's see how we can construct the representation 2, 0. So in this picture then, 2, 0, this picture. Yeah, okay, maybe I can just start from here. Let's say 2, 0. So what does this number tell you? This tells you that with respect to the first SU2 subalgebra, it's a spin 1, right? Because spin is the half of that, half of this number. So it's spin 1. And with respect to second SU2 subalgebra, it is spin 0. Okay? So the only thing I can apply here is x minus alpha 1. X minus alpha 2 will annihilate it because the singlet, so nothing happens to it. But when I apply, so this is something I just erased, the alpha 1 was, I think, 2 minus 1, right? And alpha 2 was minus 1 comma 2, correct? Minus 1 comma 2. Okay. So if I apply minus alpha 1, I will get, so I have to subtract this from here, right? So I will get here 0 plus 1. Okay. But since I know this is spin 1 with respect to this SU2 subalgebra, I can apply one more. I mean, this is the, there will be 2, 0, and minus 2. Okay? So then once more I apply x minus alpha 1, I will get here minus 2 and plus 2, right? Plus 2. So I'm subtracting from here and subtracting this. So I'll do that. That's it. This SU2 chain has stopped there. Because I knew that this is already this spin 1. So it can have only 3 states generated by this SU2. Okay. But the moment I arrive here, you see this integer is not 0. That means this is a doublet of second SU2. Half, spin half. Right? So I should be able to apply x minus alpha 2 here. Okay. Now alpha 2, so what will I get? I will get here 1 and 1 minus 2. So minus 1, right? That's that. And it stops here. It cannot go because I know this is spin half. So this is a doublet as far as this SU2 is concerned. So now here, we arrive here. This is spin half with respect to the first SU2. Okay. So I come here, subtract x minus alpha 1. X minus alpha 1, so it will be minus 1 and 0. Correct? Minus 1 and 0, right? Okay, that is that. Now look at here. This SU2 subalgebra, SUX alpha 1 subalgebra is stopped there, right? It cannot do anything. But now look at this quantum number. This is spin 1 of second SU2. So I apply x minus alpha 2. I will get again the same weight. And let's see, subtract that. No, this is not. Oh, sorry, I'm subtracting this. Subtracting this. So it gives you minus 1 and 2 cancels, right? That. But this is spin 1, so I should go once more. X minus alpha 2. X minus alpha 2. And you end up with 0 and minus 2. That's it. This is 6-dimensional representation. Because now you see this is 0. So here x alpha 1 cannot act. And this chain has stopped anyway because this was spin 1. That's it. Now here you can see, to arrive here I have 2 ways of arriving. So you might wonder the multiplicity could be 2. No? But that's not possible because if the multiplicity of this was 2, see this one SU2 doublet. Okay? It cannot be that in this doublet there is one state which has 2 multiplicities and there is 1 multiplicity. It must be the same multiplicity. Okay? So that way you arrive. And now if you draw the picture of this here in the same picture, so what are we doing? This becomes very messy. So I'm taking twice this, right? Twice this. Because this was, fundamental was 1, 0, now it's 2, 0. So it's twice that. So this one comes, twice is somewhere here. Not all the way. This is the 3 equal parts of the diagonal. So this is kind of somewhere here. This is horrible. Maybe I should erase this again and try to draw it because it's not visible. So here was a joint. Roots. My roots we need to draw, otherwise it's hard to see what is happening. Okay, and then here we said this fundamental was somewhere here. Here. This is the fundamental W. But now we are taking twice this W, so it is here. Right? I mean twice because this is half of that. I mean if I've not drawn the picture correctly here, something like this. So this is half of that. So I'm taking twice, so it should be just vertically above that. And now you apply x minus alpha 1. So this we said is perpendicular to the alpha 2, so this is singlet. That was the first state, 2, 0. Right? Now I apply 2 x minus alpha 1s because now it's spin 1. So I apply 2 x minus 1s. So I will come here and then I will go over here. Okay? So this and this. Maybe I should put a cross here to this now, this new representation. So that is this 3. This 1, 2, 3. These things, this I have covered. Huh? Now, coming here, now this becomes a doublet of this SU2. Okay? So I apply a lowering operator. So I'm going to come here. It's going to be something like this here. There will be that. And then I apply, so now this chain is finished because this was a doublet. So if you apply a further lowering operator here, it should annihilate it because it's a doublet to that, right? But now we see that this is a doublet of the x minus alpha 1. of this SU2. Okay. So I apply x minus alpha 1, I come here somewhere, and this will be another state here. Okay, now again we go back here, we went back here, because this chain has stopped, but you have to ask the question, what happens to the second chain, second SU2 chain. Now it's a spin 1 of that. From plus 2 you see there's spin 1. So I start applying lowering operators here. So the first one I apply, I arrive again exactly the same place. Second one I apply, I come here. That's it. So this is a 6-dimensional representation.
Why we just determine to be, for example, singlet or doublet, and we say we cannot apply more. So
this is from the knowledge of SU2, because we already know from the SU2. If I have a...
Okay, so and there is no specific reason connected to I mean, we applied first alpha, not minus alpha 1.
Yeah.
Then minus alpha 1.
Yeah.
For example, where we should apply minus alpha 2 in the
Here.
middle element. In the middle element.
But I'm applying here, yeah. I'm doing that here. I mean, you see that this way all is alpha 2. Here is alpha 1, this direction. I'm just drawing it like that. Huh? So, okay, let me repeat the logic again. Here, the only thing I can apply is x minus alpha 1, because from this is a singlet of x alpha 2. This you agree, right?
Yeah,
Okay. So I come here. Okay, the fact that it is spin 1, I know that I can apply this guy 2 times. Right? So I have these states. Now look at each of these states and ask the question, what happens when I apply x minus alpha 2? Right? Now you see from this number, you immediately see that this is spin half of the second SU2 algebra.
I see.
So I can apply only once, and then this chain stops. Right? Here it's a the plus 2 means it's a spin 1. So I can apply 2 times, and then it stops here. Okay? Now look at here. Here, if I okay, this chain has stopped, but now I have to ask what happens with the x. This chain alpha 2 chain has stopped. Now I want to ask what happens to x minus alpha 1. Well, this number tells me it's a spin half. So I should be able to apply x minus alpha 1, and I get here. Okay? But this was already coming from there, in this chain. So of course, there could be a possibility that there are 2 linearly independent states. This way of coming here, or this way of coming here, may perhaps give you 2 different states. In that case, this will have a degeneracy of 2, not 1. No? But that is not possible, because this whole thing is a spin half representation of this algebra. It cannot be that there is only 1 state here and there are 2 states here. No? In every SU2 representation should be for every equal number of positive and negative quantum numbers must be there. J3 quantum numbers. No, it's not possible. So therefore, we know that actually this way of arriving here or this way of arriving here, they are not linearly independent. They must be proportional to each other. Okay? So in this case, we didn't have to do this calculation, but sometimes just by these considerations you cannot decide. There you have to really sit down and check whether they are linearly independent or not. Okay, maybe later on next week I'll try to give you some example where something like that happens, and show you how you can do this calculation. Okay, and then you can keep having fun. I mean, you know.
There is also a conjugate version of this.
Yeah. This also there's no
Like the previous.
exactly. So this will be, I don't know which one is called, I'm not completely sure. So this is, we say this is a 6-dimensional representation. Then there is another one, which is 0, 2, which will be also 6-dimensional representation. But again, one of them is, one uses a bar, maybe this one, I'm not sure. In one of them, conventionally, you use bar to distinguish that these 2 are complex conjugate with each other. Yeah.
And how did you know that as joint one is 1, 1?
Because from this, we already said that this is for this choice of our simple roots, this is the highest weight. And look at the quantum numbers for H1, H2 of this. This is 1, 1.
In H1, H2?
In H1, H2 basis, yeah. I mean, for this analysis, it's better to use H1, H2 basis. Why? Because H1 and H2 are exactly appearing in the two SU2 subalgebras. You know, the reason is because X alpha 1, X minus alpha 1 commutator involves H1, I think maybe 2H1, I'm not sure, some number times H1, right? Whereas X alpha 2, with X minus alpha 2 involves H2. So for this SU2 subalgebra, this is the J3 element, right? And for this SU2 algebra, this is the J3. So the quantum numbers of these guys are directly relevant to decide which representations of these different SU2 subalgebras we are talking about, right? Whereas lambda 8 is not. Lambda 8 is not a J3 of anything. So one should choose some J3 of some given SU2, right? And then you write the quantum numbers of that.
But to promote it, lambda 8 would be better.
Well, that is just to get some nice pictures. You could have also plotted an H1, H2. No? The qualitative pictures will be the same, but in this way, it's easier to remember because you have these nice patterns. Otherwise, there's no particular reason. Yeah, we could have just worked with H1, H2 basis.
But the symmetry, Weyl symmetry is...
Yeah, Weyl symmetry we want to define it in a different way. I mean, we will discuss it when we discuss generally.
But just reflecting...
yeah, reflecting, but it's...
useful only in lambda 8 or in both?
No, you can define a general notion of reflection. Not
Maybe
this.
it won't be simple as reflecting on a lot when we use H1 and H2.
Yeah, no, you can define an operator which is equivalent to reflection. Basically, it will be, you can define. And we'll discuss in general later. Because anyway, beyond SU3, it's impossible to draw any pictures, nice pictures. SU4, you need a three-dimensional picture. We can't draw it on a blackboard. So at that point, the pictures disappear. I mean, you have to just be able to write equations. But in SU3, you can still visualize. So that is nice to see. Okay. Yeah, just the last comment I make. Now this is 2, 0, right? Well, this is 2 times that, right? So you would say that if I take the tensor product of a, now let's go back to the tensor product. Remember we discussed in SU2. Take a spin J and a spin J prime, take the tensor product of that, and then you can decompose in terms of irreducible representations. J plus J prime to J minus J prime, right? The modulus of J minus J prime. The different representations will appear. Now, if I take a tensor product of this representation with itself, okay? So I'm looking at 3 times 3. So I'm looking at this 3 times 3 tensor product. Okay. How many states will there be? Well, each of them is dimension 3. So total dimension will be 3 times 3, right? So the dimension of this representation of this is 9. 3 times 3, 9, right? Now, what about the weights? I mean, this will be reducible, just like in SU2 case, tensor product was reducible, right? But we can certainly write down all the weights. Remember the way we discussed the spin J with spin J prime. We wrote down all the H eigenvalues, right? And saw at each eigenvalue how many states are there, right? Then we removed the biggest irreducible representation. Then you looked at the remaining, and you see what is the biggest irreducible representation, and so on. And this way, systematically, we could get the full thing. The same thing I could do here. So I have 3 times 3. Now the weights of the fundamental of the 3 representations were this. This one here. Maybe I should draw it. Okay, this one, and this one, and this one. Right? This was for this triplet representation. These crosses were the 6-dimensional representation. Right? Okay. Now I take the product of these states. So I have 9 states, but the weights will always add. Right? This is clear, right? This part is clear. When I take the tensor product, the weights are going to add. For example, let's suppose in general, I have 2 representations, R1, tensor R2. Right? And these guys have some weights W's, and these guys have some weights W primes. Okay? So now let us consider a state. I mean, this I want to repeat this again and again because this is really very important concept. No? This addition of weights. So I'm repeating this many times. So please don't get bored up, because I think some of you might get bored up of this repetition. So I can take a state which is, a tensor product means it's a product of two states, right? State from here and a state from there. So I take a state with the weight, which is an eigenstate, times a state which is an eigenstate of the kappa here. So I to look at that. Now I apply R of H on this state. Now R is this big representation, tensor product representation. But I know how it acts on this is by additive, right? At the Lie algebra level, it acts as sum of two terms, right? So this acting on that is the same as R1, the first representation, acting on this guy times W prime plus W times R2 H acting on W prime. That is the definition of the way, that's the way the Lie algebra elements acts, right? Because Lie algebra elements are infinitesimal. The group elements act simultaneously. But when you look at the infinitesimal, it just becomes additive. The two, this is an infinitesimal from the first guy, this is an infinitesimal from the second guy. Okay? So now if this is already eigenstates, this is going to be, let's say, W of H times W, and then of course tensor product W prime. And this guy is again an eigenstate with W prime weight. So you will, and it's a number, so I can take it out. So you get W prime H at the same state. Okay. So it's sum of these two terms. Huh? So you see, this is the same. So the weights are just adding up. So it tells you that in a tensor product, just take these vectors and add them up. Right? So let's see what are the states. For this one, you see, there is only one way of getting it, right? So now I'm taking 3 times 3. So I have to take all possibilities. So I can take this state from here and the same state from there, right? In that case, the weights will add and you will end up there. This was 1, 0, and now it will become 2, 0. I mean, I'm still using this notation, okay? Not in the lambda 8 language, although I'm plotting it in the lambda 8 language, but I'm labeling them by H1, H2. That's just true. Otherwise, all these root 3's will be floating around, so I don't want to write root 3's. Right. That's what this is certainly. So if you look at the number of states, so at the level of 2, 0, we have only one state. So let's write down what are all these states here. Do you remember? Yeah, I didn't. Yeah, 1, 0. We had in the triplet, what were the weights? 1, 0 is the highest weight. And then we had subtracting this 2 minus 1. So it will be minus 1, 1, right? Sorry? Oh, no, this is coming from outside. And then finally, this one here. So that was subtract 0 and minus 2. 0 minus 2. Correct. So these were the 3 weights, right? So I took care of this with itself. So that gave me, so in the tensor product, in this product, the weights are, I should find 9 states, right? So one of them is 2, 0, and there is only one state, right?
0 minus 1.
Maybe I made a mistake.
Because it's applying alpha 2.
0 minus 1.
0 minus 2, right? I mean, I subtract. So this is alpha 1.
It's 1 minus 2.
And this is, correct. 0 minus 1, correct. 1 minus 2, correct. 0 minus 1. Exactly. Okay, thanks. So there's one state here. Now let's look at a state, this one coming from here and that one coming from there. Okay. So that will have, just add the weight, so it will be 0, 1. But there are 2 possibilities here. I could take this from this, that guy, from this, that guy, or vice versa, right? So clearly multiplicity here is 2 states. This is not irreducible. This is reducible now. Now I can take, say, this with that. Okay. Again, there are 2 possible. 2 multiplicity will be 2, and this time I will get 1 minus 1. Or I can take this with this, which will be minus 1, 0. Again, multiplicity 2. Then I can take this times itself and this times itself. So those are that will be a state minus 2, 2. This is a multiplicity 1 and 0 minus 2 multiplicity 1. So that way we covered all the 9 states. Now if you look at this one here, so certainly what is the highest weight state here? The highest weight state is clearly that, 2, 0. Nothing more than that, 2, 0. Okay? So 2, 0, so I know for sure there is this representation that we talked about. But these are all multiplicity 1. So once I take out that representation, so I can cross out, this guy has gone. One of these 2 states have gone, right? So what is left over, this has gone and only 1 is left over. This is gone completely. 1 minus 1, again, one of these states has gone. So only 1 left. And similarly, minus 1, 0, one state has gone. So there's only 1 left. And the minus 2, 2 and 0 minus 2, that have gone out completely. There's only 1 state and that has already gone. Okay. So that is 6 states are appearing in this in this representation, in the 6-dimensional representation, 2, 0. What is left over? 1 each of these 3 states. But that was exactly what we call 3 bar. You see here the highest weight is 0, 1. Okay? So once you have removed this guy, then the remaining 3, now you ask what is the highest weight here among these 3? Then you find this is the one. And that corresponds to that. 3 bar. Okay? So the conclusion is the tensor product, this 3 cross 3, splits into irreducible representations, 6 plus 3 bar. So that, of course, I mean, this is, I mean, I prefer to, I mean, you see, conceptually this is what is happening. If you want to use this for some higher dimensional representation, very high dimension, it'll be intractable, right? I mean, you know, but this is the concept behind it. This is the main idea behind it. Okay. For high dimensional representations, you cannot, you'll take weeks to just try to write down all these weights and group them, etc. There are quicker ways of doing it, Young tableau and all that. But when you do Young tableau, you don't understand the concept. Why this is happening? I mean, the set of recipes. You just follow those recipes, you get the answer. But this is the real reason behind it.
So, and if you were to plot 3 times 3, it would be like those crosses and the inverse of the... Exactly. So exactly. So here was the multiplicity 2. These 3 states had this multiplicity 2. So when you take the 6-dimensional representation, you take one of them, or then what is left over is this triangle, which is exactly the opposite. And they fall into the same box.
Same. Yeah, you saw the multiplicity. Yeah. So 6 and 3 bar. You can try, I mean, just try it during the weekend to do 3 times 3 bar. 3 times 3 bar. 3 times 3 bar, just try it using this procedure. 3 times 3 bar. Okay. So this was highest weight 1, 0, and this was highest weight 0, 1. Okay. This will be 9 states, and I'll just tell you the answer and just try to verify that. So here are 9 states. Again, dimension is 3 and 3, so 3 times 3, 9. And it splits into the adjoint plus a singlet. Plus a singlet of SU3. That's how it will split. The adjoint representation and the singlet. But singlet you already knew. Because remember, when we discussed the complex conjugate, this is the complex conjugate representation of that. We saw that from that you can always construct an invariant, which under the group is invariant, right? And that invariant is this. But then there are 8 more states from then out of this. These 8 states join together to form the adjoint representation. You can just try to do that, just adding the same way, just doing that. Okay. And, just list all the weights and then see that. Look at all the highest possible weight there. And from there you immediately see that you will find there is a 1, 1. In fact, you can see, when you add that up, you will get a 1, 1. And 1, 1 is directly a joint representation. But just check if all the other weights agree. No? It had to agree, but okay, just to check. Okay. So, anything else? Yeah, okay. Maybe tomorrow, maybe I may have forgotten several things here. So I will try to recap, to talk about them. If you have any questions, we can discuss that. And then, yeah, maybe I can also mention a little bit of young tableau. Yeah, I mean, because you can. This representation is also quite interesting. Physics-wise, this is quite an important tensor product. This is basically gives you the meson, all the mesons. Because mesons are made up of quark and anti-quark. Okay. So it's a bound state of quark and anti-quark. Quark transforms as a triplet. Anti-quark transforms as a complex conjugate. So anti-quark transforms as 3 bar. And you take the product, and again, I'm not here talking about SU3 color. I'm just talking about SU3 flavor, like what Gelman did. So you put the U, D, and S. These 3, ignore their masses, okay, and ignore the charges and so on, and just look at the structure. So this QQ bar will be exactly this thing. And this will split into, as we said, 8 plus 1. And those 8, this is, yeah. Yeah, there was a very, I mean, I'll just tell you some, there was a very kind of an interesting thing that the mesons were, so these mesons were pi plus, minus, pi naught, pi meson. Yeah, have you heard of these names? Have you heard these names? Anyway, you will see that in the particle physics course. These names, if you don't. And then K plus, K minus, K0, K0 bar. This is already 7. Then there is a 1 eta, some other particle. So all of these are inside here. But then there is another eta prime. That is this one. I don't know, maybe I'm not saying the correct notation. But it's, so there are 8 mesons like that, but there is one which is sitting out, which is not in the same representation. Okay? And then there was a puzzle for a long time that somehow this was behaving in a very different way. I mean, in other words, of course, you see, strictly speaking, they are not, their masses are different. U, D, so this U, D, and S, there are masses are not the same. So you don't expect all of these guys to have the same mass. So it's not an exact symmetry, no? It's an approximate symmetry. Right? So all of these 8, if there was an exact symmetry, all these 8 states must have identical mass, right? Identical charge, everything, but it's not. But I mean, approximately, they had more or less masses which are not very far from each other. But this guy behaved very differently. They had very different mass and so on. This was what was called the U1 problem. There was a U1 problem, and which was, it had a beautiful solution in the late 70s, given by 't Hooft, who is one of the great scientists, high energy physicists, 't Hooft. So 't Hooft gave an explanation for this. And that explanation comes out to be extremely beautiful. It was it really uses a lot of structure of the quantum field theory. In particular, non-perturbative aspects of quantum field theory. It's a very, very beautiful paper. That is just, this was in the 70s, So you see this problem even then. I mean, it survived for so many decades, Mesons were discovered long before that, But that problem was finally solved in the 70s only. Okay, so so this is the and the other thing that which is much more complicated is take 3 cross 3 cross 3. What are these? Why is it important? Because now you say again, think in terms of quark, they're all 3, not 3 bar. So it's like 3 quarks, but you know what it is? It's a baryons. Proton, neutron, all of these things, right? So again, it's nice to see. They are quite important in physics. I mean, particle physics at least. Okay. So I will then see you tomorrow.